So I know that current across the power supply squared is equal to the current across the resistance squared plus IL minus IC squared. Let's find the impedance.
One
Z
over,
did somewhere.
1 over the square root of r squared.
Oh, you're just jumping straight to it?
Yeah.
Let's do the intermediate steps first.
So you just, like, that'll be v over impedance squared. And then voltage over resistance squared. And that's voltage over the XC, I don't remember the name.
L, XL.
XL.
Inductive reactance. Minus. Sorry, spoiler. Okay, now what?
You take out all of the voltages.
Because they're all equal to each other. So we end up with 1 over Z squared is equal to 1 over R squared plus 1 over XL squared minus 1 over, nope. 1 over XL minus 1 over XC. That whole thing squared. And so Z is equal to 1 over the square root of 1 over R squared plus 1 over omega L minus 1 omega C quantity squared.
Now, for most problems, do we have to go through all those steps, or can we just go straight to that last equation? If you know the numbers, like if you know how it's gonna turn out.
If you know it's an RLC parallel AC circuit, then yeah, that's gonna be the impedance.
Okay.
But if I give you something slightly different, do not go through that equation.
And are we always going to be solving for impedance?
A great deal of the time.
Now I'm confused. I thought we put omega L in the so now why is omega C without the 1 over?
Because I got 1 over X sub C here.
Yeah.
And so I'm taking the reciprocal of X. So 1 over X sub C is 1 over 1 over omega C, which is omega C.
Oh, okay. Got it.
Despite what I wrote on the board earlier.
Okay. And then because XL it's just omega L, not 1 over.
Correct.
Got it.
All right, let's do some numbers. Let's figure out some phases. So again, we'll make this 60 ohms. We'll make this 30 millifarads. And for this, let's make it, let's see, so it's gonna be omega L. And let's make this 20 millihenries. I think that'll work. Let's find out.
And our frequency?
milliamperes, so that's what you're dealing with tomorrow. So omega is 377.0 something. Three
76.991.
76.991, okay. That's radians per second. And so we need to identify the phase, so let's just assume that the voltage phasor has a phase shift of 0. So the voltage phasor for the power supply, so phi of power supply equals 0. Let's see if we can come up with all 8 equations. So, step by step. All right, so we know enough, I do need to give one other bit of information here. Let's say that the RMS value, the voltage for the epsilons of RMS is equal to, we'll make it 100 volts.
What does that mean?
Root mean square, it's basically, it's an average. It's a way of finding the average for something that's oscillating back and forth between positive and negative. So, we now have enough information. What is epsilon sub naught then?
It's not permittivity of free space, correct?
Excuse me?
It's not permittivity.
It is not. If we were dealing with permittivity of free space, then electric fields would be coming into the conversation. We are not dealing with electric fields, not in the same way that we have been. So, how do you find the maximum value? How do you find an amplitude if you know the average?
Undo.
Yeah. Undo it with 500.
There's a simple factor.
Multiply by 2.
Close,
Divide by 2.
farther away.
Oh, square.
Square.
Square it.
Square rooted. It's just the RMS value times the square root of 2. So that, therefore, this is 141.414 volts. It is 1.414. Okay. All right, so we now know the equation for epsilon, the voltage for the power supply. So the voltage for the power supply is equal to 141.4 volts times the cosine of 376.991 radians per second times time plus 0. Matter of fact, we know more than that because it's a parallel circuit. So that would also be the voltage for the resistor, which is equal to the voltage for the across the capacitor, which is the voltage across the inductor.
Wait, but didn't we say that all of those are equal to epsilon sub naught?
That's the same.
But the phasors are all the same.
Oh, but the values aren't.
Well, if the phasors are identical, then, yeah, the magnitudes are all the same as is listed right here, but since the phasors are all on top of each other, their instantaneous values would be the same every time, the entire time.
Wait, now I'm confused.
But
When we're saying, the voltage of the power supply, that's the same thing as saying, that epsilon sub naught?
The epsilon sub, that's epsilon sub naught is the amplitude.
Then how is that, how is you see where we have equal?
Yeah.
What's that epsilon sub naught then?
That's the same as that epsilon sub naught. This is the amplitude of the voltage phasor.
At its maximum.
And it's the amplitude all the time, but, yes, it is the value of the power supply voltage at its maximum.
So then why is,
When we add the cosine times 376 times time, how does that still equal the
to just
141?
1.4?
We're saying that if epsilon,
How'd you get that?
no, the epsilon sub 0,
Yes, epsilon sub 0.
so that is equal to all of those, and you multiply it by 376 times time, how is it still equal to those three other values?
At any moment in time, I'm not saying this is not a direct current at all, it's constantly fluctuating. What I'm saying is that at the maximum value of the voltage across the power supply is this. When the voltage across the power supply is this, that also is the voltage across this, this, and this, because they're in parallel. At some time later, the value is going to be less, so why don't we just pick at, right to that.
Oh, because if time is 0, then it just ends up being that value, I guess.
Yeah, when time is 0. So if we had time is equal to 0.01 seconds, then the value of the power supply is 141.4 volts times the cosine of 33.76991, which is negative something, I think.
Because in the last problem, we had time is equal to 0, now we have time is equal to some number, or,
Here, yeah.
yeah, okay.
The whole point, before when I said time is equal to 0, that was just to establish what the phase shift is, what the value of phi was.
It's negative 114.395.
Units?
Volts.
So the voltage, so at 100th of a second, the voltage of the power supply is negative 114.395 volts. At that moment, the voltage across the capacitor, the inductor, and the resistor are the same. Because again, parallel structure, at any moment, the voltages are equal. What'd you get?
114.1523.
Oh, you differed in this?
Yeah.
Okay. I suspect there's a rounding somewhere.
3.76991.
3.76991. Did you use a fuller value or use that
I
number?
used the same value.
That, he's right most of the time.
I probably would not notice on a quiz or test that difference.
My calculator is fucking. Well, he's probably using a calculator, not using Cosmos.
That's what I'm using.
Oh, I put.
Yep, found it.
Okay.
Definitely a me thing.
I'm noticing a pattern here. Other questions before we start finding currents? All right. So let's find some currents. I have 4 different current phasors. That means I'm going to have 4 different equations. I know, well, first off, I know this is in phase, the current for the resistor is in phase with the voltage for the resistor, so they will have the same phase angle. So the current across the resistor is gonna be equal to some number, we'll just, instead of doing an underline there, capital I sub R cosine of 376.991 radians per second times time. The fact that it is in phase tells us that the phase angle is the same. So since the phase angle here is 0, the phase angle here is 0. We just have to figure out what big IR is. Well, I know that VR is equal to IR times R, our Ohm's law variation. I know that VR, that's the amplitude of the voltage for the resistor, is 141.4 volts. And that's going to be equal to IR times my resistance, which is 60 ohms. And so therefore my current, magnitude of my current is 2 point something.
2.356 repeating.
2.356
No, 6 is repeating.
units.
Amperes.
So I now have my current phasor for the resistor. So let's write up what we know here. So my voltage for the power supply equals 141.4 volts cosine of 376.991 radians per second times time. And I now have the current for the resistor is 2.356 repeating, 356 repeating amperes cosine 376.991 radians per second.
Why? Oh, never mind.
I just realized that we were all solving for big I and not little I.
Yes.
Got it.
But in finding big I, we know what little I is.
Indeed.
All right. Now I've got, again, we'll do the power supply last. I need to figure out IL and IC. Well, what's going to be the phase shift for I sub C?
90, so we just put 90 in front of T.
Put 90 instead of C.
T.
T.
In front.
No.
Need to be radians or degrees.
We prefer radians.
So it would be plus pi over 2.
Yeah, you're gonna add it to it. So we end up with, so the current for the capacitor is gonna be I sub C, we don't know what I sub C is quite yet, times the cosine of 376.991 T plus pi over 2.
And then, so we would do 1.4 equals, yeah, okay.
So 141.4 equals I sub C times my capacitive reactance. There's just a straight up formula for it, 1 over omega C, omega being 376.991, and C being 0.0, try that one again, 3 times 10 to the negative fifth. And the answer is go for it. What did you get?
1.59919.
said?
Yeah.
You get the same thing? Woohoo!
Curse is gone.
So the current for the capacitor is going to be 1.59919 amperes times the cosine of 376.991 T plus pi over 2. One more to go, and then we're gonna check our answers. All right, so for the inductor, I sub L is gonna be big I sub L cosine of 376.991 T. Sorry, we have 2 more to go.
Minus pi over 2.
Good, minus pi over 2. I sub L, I know that V sub L is equal to I sub L X sub L. So I sub L is going to be 141.4 divided by omega L 376.991 times 0.02.
Millihenries to 20 millihenries to normal henries is 0.02.
Yeah, milli to regular, you move 3 places. Oh, got it.
18.7577.
18.7577? Yeah. All right, now, if you just look at what we have here, would be volt seconds per Henry, otherwise known as